And take 2. Identifying exponential functions. So we are looking at exponential functions more closely. You've seen them already with transformations, right? We moved them around a little bit when we were talking about transformation. But now we're going to look at what every piece of the exponential function means, how we can solve exponential functions, how we can graph exponential functions, what they really do for us mathematically. Today we're just going to kind of look at them and get used to working with them. So when you see an exponential function, the easiest way to recognize that it's an exponential function is that the x, the variable, is actually physically up in the exponent. So in order for it to be an exponential function, the exponent has to be a variable. The other thing that we notice is that it's normally in this form, a times b to some variable plus c, where a is just going to be a number that represents our initial value. So a is how much money we're putting into our bank account to start with before we start collecting interest. A is how many people come to school with the flu initially before they spread it to everybody else. It's however many we're starting with. So A is our initial value. How many we're starting with. B is our growth rate. So that's how fast it's spreading, how fast your money is increasing. If we're talking about half-life of chemicals in chemistry, how fast they're decaying, right? It's how fast the thing is changing. This is your growth rate. And then C is your asymptote. So we know that the exponential function kind of looks like a little bit of a swoosh sign, a little curve that flattens out at the bottom. That C tells us our end-all, be-all. We cannot go lower than that, or we cannot go higher if it's decay. This is our asymptote. So our asymptote is going to be things like if we were talking about the money in your bank account, you put $100 in your bank account, and you just leave it in there to collect money, you're never going to have lower than $0 because it's a savings account. You're not going to withdraw from it so that you can have negative. They would only let you take out what you have, so you could never have lower than 0. So in that situation, your asymptote would be 0 because that would be the least amount of money you could ever have in your savings account. So our asymptote is kind of like our cutoff point. We can't go past that, and we know that because we know we can't cross over asymptotes. So it's a way for us to help identify which equations match with which graphs, because it's our flattening off point, it's our leveling point on that graph. So let's look at one of our most common exponential functions and talk a little bit more about it. So let's identify parts of f of x equals 2 to the x, and then we're going to draw a picture of the graph. So f of x equals 2 to the x looks very similar to the function we were working with when we were doing transformations way back in the beginning of the school year. This is our situation where something is doubling. So our growth rate here is 2. And I know that because that's the number stuck to that exponent. So my growth rate always has to be the number stuck to the exponent. That's how fast the function is changing. The bigger the number, obviously the faster it'll grow. The smaller the number, the slower. Do I have anything else going on in that function? No, right? I'm not adding anything. I'm not multiplying anything out in front. Not at least that I can see, right? But if I took this and I added in a plus 0, I'm not changing it, right? So if you're not physically adding anything at the end of the equation and it asks you to find the asymptote's just 0 because there's nothing being added or subtracted there. So in this situation, my asymptote is going to be y equals 0, because it's a horizontal asymptote. So anytime we're writing this, we're writing it as an equation, y equals 0. So on your homework, or not your homework, your classwork today, when you're doing that and it asks you for the asymptote, make sure you don't just give me a number, you have to give me y equals, so that I know you know it's horizontal, not vertical. And then, if I asked you for the initial value here, we don't have anything out in front of that 2, but the reason we don't have anything out in front of that 2 is because I'm really just multiplying by a 1, and we know mathematically we don't have to represent that. It's not going to change anything. So when there's no...
Pardon the interruption. Jazon Stevens, please report to the main office.
When there's no number out in front, that's just our initial value of 1. So if I'm going to graph this, I'm going to put in my x-axis and my y-axis. I know that I can't cross over the x-axis because I have an asymptote at 1. So I could go in and remind myself of that and just turn this into my asymptote, right? This is my y equals 0 asymptote. I have an initial value of 1. I have a growth rate of 2. Do you remember kind of what the general shape of an exponential function was? It was kind of like that little swooshing, looked almost like if you were going to make a big E, it looked like the beginning part of the E. So we kind of know the general shape. Before we go and actually draw this, though, we want to find the y-intercept. So then we can actually physically plot a point so we know where it's starting. So we want to find the y-intercept. And we know y-intercept just means that x is 0. So our y-intercept is always some kind of point, 0 comma something. If x is 0, in order to find my y value, all I'm going to do is take my equation of 2x, and I'm going to plug in 0. And 2 to the 0 power just gives me 1. Right? Anything to the 0 power is 1. So that means when I plug in 0, I get out 1. And my function is going to flatten out as I get closer to 0. And it's going to increase as I go to the right. If I wanted to be super accurate, I could plug in some extra x values, or if I forgot what the general shape of an exponential function was, I could plug in some x values and get more points and plot the points and connect the dots. You can always do that if you forget what your parent functions look like. But just in general, now we have an idea of what the picture looks like. So we have 2 different situations when we're talking about exponential functions. We can have exponential growth.
Please excuse the interruption. Ms. McCarthy, please contact the main office.
Exponential growth is any time that your growth rate is bigger than 1. So looking at the equation, if you had an actual value for your b that was bigger than 1, that's going to be exponential growth. So you could have things like f of x equals 2 to the x. You could have f of x equals 7 times 4 to the x minus 5. You could even have f of x equals 1/2 times 3 to the x plus 2. It's that number stuck to the x has to be bigger than 1, which tells you have exponential growth. And your exponential growth graphs will always look like your parent function. They will always be in some form starting off slow and then speeding up. So it's a good way for you to be able to check yourself, because your classwork today is going to give you an equation and ask you to find a picture of the graph and explain the different pieces of the equation. So if you see that the growth rate is a whole number bigger than 1 or any number bigger than 1, the graph's got to be going up. That's exponential growth. If you see that the growth rate is less than 1, so things like f of x equals 1/4 to the x, f of x equals 2 times 1/3 to the x. Anytime you're working with a fraction less than 1, then you're going to have exponential decay, which means you're starting off slow, but instead of growing exponentially, now you're decreasing exponentially. So your graphs for exponential decay are the opposite. They slowly grow at the end. Think about it like when you're talking about in chemistry, when they talk about half-life of elements. If you started with a giant chunk, you broke it in half, you lost a lot right away, and then you kept losing smaller and smaller pieces because every time you took half of it, the piece that you were working with was smaller. So the big stuff happens at the beginning when you're talking about decay. So your classwork today is going to give you an equation, ask you to find the initial value, ask you to find the growth rate, ask you to find the asymptote, and then ask you to match it to a picture of the graph. Another way you could match it to a picture of the graph if you weren't totally sure is to bust out Desmos, right? And get yourself a picture. All right, let's do it.